Hello everyone, welcome again. Welcome to the 5th lecture of the course Cyber Physical System Fundamentals. In this lecture I'm going to continue to try to teach you the embedded systems fundamentals of cyber physical system design. In this lecture we are going to continue to cover the material which is presented in chapter 2 of the companion textbook, that is the chapter on specification and modeling techniques. The structure of this chapter can be seen in this table. In this table we see the different models of computation and the associated languages. Just to remind you, in one dimension we have the method that we are using for communication, and in the other dimension we have the method that we are using for the computations in the components. We have already covered the first row, and in the last lecture I have already also covered part of the second row. In particular, I talked about state charts and very briefly about synchronous languages and timed automata. Today I'm going to cover message passing combined with communicating finite state machines as the model for the components. In particular, I'm going to talk about SDL as one language which represents such a model of computation. So SDL is used here as a very prominent example of a model of computation which is based on asynchronous message passing. So from the general discussion of message passing, we know that SDL therefore is also appropriate for distributed systems. Just like state charts, SDL is based on the finite state machine model of computations, and in the context of SDL, each such finite state machine is called a process. Now, at the time SDL was designed, there was a very strong discussion between people who favored textual formats for the specification of such systems, and others favored graphical formats. In order to please both kinds of users, the designers of SDL decided to provide both formats. So first of all, we have to find a way to represent the finite state machines that are corresponding to the components. And in this context, SDL uses a special graphical representation. In order to introduce that special graphical notation, I would like to derive a special example from the corresponding representation as a finite state machine in the form of a state diagram. So the state diagram that you see in the upper part of this slide is a variant of the finite state machine state diagram that we have already seen earlier. It's a variant because we have dropped the state Z, and we have also added outputs. Now this state diagram can be very easily transformed into the corresponding representation in SDL. In the corresponding representation in SDL, these symbols denote the states, these symbols denote the inputs, and these symbols are used for the outputs, and that's again another state. Ellipses are used to indicate the default state. Now also, it's frequently a custom to have a separate column for each of the transitions in the finite state machine. So like in this case, this transition over here is represented by its own column over here. And whenever we have a transition from A to B as a result of input G, we can visualize this in the form shown in this slide. And if after this transition we will be in the new state B, and if then we would have an input of H, we would be arriving at the new state C. So this is how we can transform standard state diagrams into the graphical notation that is used for SDL. Now for SDL, communication by means of message passing is the key feature, and this is how it works. In SDL, we assume that we have a set of finite state machines. In the graphical notation, they are denoted by octagons. And for each of these finite state machines, we have an associated FIFO. So one FIFO per finite state machine. And then we can think of executing such a model by generating the outputs that are a result of transitions in the finite state machines. So for example, there is an output generated, there is another output generated, there is an input consumed, another output generated, another input consumed, output generated, input consumed, input consumed. So in order to execute the model of a SDL specification, this is what we have to do. We have to analyze each of these processes or each of these finite state machines. We have to fetch the next entry there from the FIFO. We have to check if that entry will enable a certain transition. That means if we have an edge which is labeled with that input. If that's the case, then this transition will take place. If not, that input is just ignored. There is one exception. There is a so-called save mechanism which allows us to keep track of the inputs that were consumed. Now, it's a very key idea for SDL that theoretically we assume that these FIFOs are of unlimited capacity. That means when we discuss the meaning of such a model, we will never argue about FIFOs that could be full. So that means these FIFOs have to be made large enough so that they will never be full. Which means that whenever we try to implement such a model, we will have to think about the safe upper bound on the length of the FIFO, and deriving such a safe upper bound is actually not trivial and is one of the key steps which is required when we try to implement an SDL model. Now, knowing about the typical characteristics of state charts, there is one question that we can raise immediately. It's the question, would SDL models necessarily be determinate? Now, there is one counterexample which tells us very easily that SDL models in general are not determinate. In order to demonstrate that they are not necessarily determinate, we can use this counterexample. And in this counterexample, we assume that two inputs are arriving at the same time at one of these FIFOs. Now, we don't know in which order they will be stored in this FIFO if they really arrive at exactly the same time. The only thing that we know is that none of them should get lost, so therefore we need to ensure that both get stored. The order in which they get stored is not known beforehand, and obviously we can very easily come up with examples that demonstrate that the behavior of this process 3 will depend on the order in which we have stored these inputs there into the FIFO. All these orders are legal. The simulators can show different behaviors depending on the order which we are selecting, and all of these orders are correct, all of these behaviors are correct, and that means obviously that SDL models don't need to be determinate. That's a practical problem that designers are faced with. Now, SDL also supports operations on data. If you would like to operate on data, you would usually need variables. Variables can be declared locally for each of these processes. These variables can be either of predefined type, or they can be of a type that's defined in SDL itself. So in this particular example, we see variables counter and integer, which are of predefined types integer and string. yeah, these were these variables counter and date there are of type integer and string. So on these variables we can have a number of operations. For example, we can have arithmetic operations, we can have assignments, and we can check for the values that we have at a particular moment in time for these variables, and depending on the values we can have kind of case statements, like in this case where we are branching into a particular direction as a result of having a particular value stored there in this variable. Now for SDL we also need to support hierarchy, and the question may be, how do we support hierarchy in SDL? Well, in order to model hierarchy in SDL, we can model the different types of communication, the exchange of information between the different processes or finite state machines. Like in this case where we have communication between processes P1 and P2, and it is assumed that we can send signals, these are outputs of process P1, to this process P2. The sending of these inputs and outputs always has to be via channels, and these channels are labeled, they have certain names. So in this case this is a channel SW1 and this is a channel SW2, and if we would be sending this signal B, then it would need to go via channel SW1, because as this annotation is indicating, signal B will never travel across this channel SW2. The signals that we are using can be declared locally in such a graphical description. This graphical description is called a process interaction diagram, obviously because it describes the interaction between processes. These process interaction diagrams are a special case of so-called block diagrams. Block diagrams are diagrams that describe the communication between different processes or also different blocks. These process interaction diagrams can be used at the next higher level in the hierarchy as components. So we have this block B1 here as a component at the next higher level in the hierarchy, and in addition we have another block there. So overall we are arriving at a hierarchy where we have this block at some level there in the hierarchy. At the next lower level we have these process interaction diagrams as I introduced them on the previous slide, and as leaf nodes in this tree we have the different processes or finite state machines, and at the very top level of this hierarchy we have a block which is called the system. So we have this close link between these nodes there in this tree and these graphical descriptions of the hierarchy in SDL. And also we have obviously this very close link between this node here in the tree and the graphical description in SDL. Now for SDL we also need to model time, so therefore it is supported to model timers. Obviously it makes a lot of sense to have timers as a language element that's attached to the different processes or finite state machines. Therefore timers can be declared locally. So in this case we see that there is a timer which is declared locally, and for these timers there are certain operations that are supported. So for example we can set timer values. This particular call will set the timer value to the current time plus some offset, and this will be linked to this timer t. So if that transition takes place we will be setting that time. If this amount of time has elapsed, a corresponding signal will be put into the FIFO queue of that finite state machine. And suppose that we are in this state E and this timer elapses, then we will have the corresponding transition. If before this timer elapses we have an input event of F, we will be following that other transition and resetting the timer. Now we have seen that these timer signals are put into the FIFO queue, which means that these timer events are not taken care of necessarily immediately, because there could be already quite some inputs there in the FIFO queue, and the timer event would be processed only if processing is at its turn, and that means it could be delayed a little bit. So timers are appropriate more for soft time constraints than for hot time constraints. Now what I mentioned, what I described about the SDL serves the purpose of giving you an example of how a language that combines asynchronous message passing with finite state machine models could look like. It's not a full course on SDL, so therefore there is a large number of language elements that I'm not discussing in this lecture. These additional language elements, they include procedures, they include facilities for creating and terminating processes, and they include facilities for the advanced description of data. We will see some simple examples of that a little later. Even more features were added for SDL 2000, removing some of the earlier restrictions. Now, in order to demonstrate how we can use that example, how we can use that language, I would like to use two examples. The first example is a rather a small one, and the second one will be a little larger. So the small example is an example where we have a system that comprises three different computers or processors that are connected in a local network using some router. So you see the three different processors there. You see the channels over which we are connecting these processors. And then at the next lower level, we are describing communication within the computers or processors. You should be aware of the fact that communication using standard protocols is typically implemented using protocol stacks, and the different layers in the protocol stack, they can be visualized in these SDL diagrams. You can also see from this example that obviously there are more layers there for the computers than what we have here for the router. A router will never analyze as many layers there in the communication stack as do the different computers that also analyze, for example, the application layer. So that was a very simple example which clearly demonstrates the usefulness of SDL for modeling communication in computer networks. The second example is a somewhat larger one. This is a vending machine. It's a vending machine that serves selling pretzels, potato chips, cookies, and donuts. And this example is taken from a book by Berger, Lavia, and Rouliat. And you see the four different products that we are trying to sell over here. Now it's a American vending machine. It's designed for the US market, so it's accepting nickels, dime, quarters, and $half-dollar coins. Obviously it's not a distributed application, but we can nevertheless demonstrate how we can model systems with SDL. So first of all, let's look at the top level of the hierarchy. Let's look at the system, which is the vending machine. In the vending machine, we have a number of blocks, including the coin interface, including the decode request, and including the change interface. They are linked with each other via channels, so we have one channel that goes into this coin interface. There is another channel called C request, and there are these local channels between these different blocks. So for example, there is this channel called C add, which is directing the block decode request to add a certain amount to the amount that's considered as being input by the user. So you see that this signal add has an integer parameter over here, and this integer parameter is actually really a type int, which is a subtype of the full type integer, and the subtype corresponds to a subrange of the full range of integers. Regarding the other channels, we see that over here we have signals that correspond to the user putting in nickels, dime, quarters, and half dollars. Also, you see the different signals over here. The person in front of the machine might either try to purchase a certain product or might try to reload a certain product. Then also we see that the block decode request will instruct the coin interface possibly to reject further coins or to accept coins. We can display the amount that has been entered so far. We can turn on the display demonstrating that a certain product is no longer available. And also the block decode request can make one of these 4 products available to the customer. Down here for the coin interface, we see that there is an indication that exact change is required and some change can be returned. Now next we can look at the next lower level, and we will look at the block decode request. In this block decode request, we see different processes here. So we actually have the special case of a process interaction diagram. And we see 4 different processes for the 4 different products that we are selling. And in addition, there is an amount handler. We see over here that there is an input channel, rPretzel, where we are having signals purchase Pretzel and reload Pretzel. This rPretzel actually is a renamed channel that was also available at the next higher level in the hierarchy. You see down here from this connect statement that we are connecting rPretzels to the channel called C request. C request is the name of the channel that we are using right here at the next higher level in the hierarchy. Over here we see that the different products can be made available, or we can also announce one product to be no longer available. And down here we see the declarations that declare the different constants corresponding to the prices of the 4 different products. And also we see how many items would normally be available. Now at the next level of the hierarchy, we look at the process that corresponds to the selling of potato chips. There we see that the default state is the state purchase weight. If the customer pushes the button for this product, then we first check if enough money has been put into this vending machine. Now, since this is a local application, there is one exception to the assumption that we always communicate via message passing. Since this is a local application, it is in a very restricted way possible that we access global information through shared variables. So using this special viewed construct, we can access indeed the global variable corresponding to the amount of money that has been put in so far. And we can check whether that is at least as much as the price of potato chips. If it's not, we just go back to this state purchase weight. If it is, then we will subtract the price for potato chips. We will reduce the number of potato chips by 1, and we will provide the potato chips to the user. If as a result there are still more packages of potato chips available, then we go back to that purchase weight statement. Otherwise, we turn the indicator that no more potato chips are available on. We go to the empty state and we wait for some staff member to reload the potato chips. We assume that reloading is always to the full capacity of the vending machine. So this example demonstrates one application of SDL. Now, regarding the history of SDL, I could state that SDL is actually a very old language. It dates back to the early 1970s. Formal semantics were defined in the late 1980s. There are several standards that have been defined. They have been defined by the ITU, by the so-called International Telecommunication Union. Initially, there was the recommendation Z100, and there have been updates from time to time. SDL 2000 was a significant update. It extended SDL into different directions. However, some of the tools seem not to be supporting SDL 2000 yet. SDL 2000 might have gone a little too far, actually. Right now we are seeing SDL to become a little less popular, even though in the meantime it did certainly serve its purpose, and it was certainly successful. To wrap up and to summarize our coverage of SDL, I'd like to remind you that for SDL we are using the finite state machine model for the components, and we are using non-blocking message passing for communication. Also, it's obvious that theoretically these FIFOs should be of unlimited capacity. Whenever we really have to implement SDL, we have to find a safe upper bound on the size of the FIFO. It's obvious that SDL is excellent for distributed applications. Therefore, it was used, for example, for the design of the ISDN protocol. And I think the fact that different ISDN devices from different vendors were actually cooperating successfully with each other, I think to some extent can be attributed to the specification in SDL. Commercially available tools are listed on a corresponding website, so whenever you're interested to learn something about the available tools, you are suggested to look at that website. We have seen that SDL is not necessarily determinate. Also, we have seen that the timer concept is adequate for soft deadlines, but less so for hard deadlines. We have seen the limited way of using hierarchies. It's not possible to link different finite state machines to each of the levels in the hierarchy, but we have these finite state machines only for the leaves of the hierarchy. There is a support for different data types, but nevertheless there is still limited programming language support, so you don't have full support of an object-oriented language. And obviously there is no description of non-functional properties, so the disposability of the design products cannot be described in the language. As examples, I presented a small network and this vending machine.